MCT4C, day 40. This is part one of a two-part lesson, double lesson, different topics today. So there's two distinct videos. The first one is basically on tables and how different polynomial functions look in the table. And so the goal for today is to review finite differences, determine the degree of a given table. It asks us to fill in the tables and calculate the first, second, third, etc. differences until the differences are constant. Well, the table's not even given for us, so we actually have to, we take x is -1 and put it in there. 2 times -1 is, put that onto a calculator as -3 and so on. Now I've done that already, and I'll actually show you in a second, an easy way to do this, and probably you can do this in your head, right? X is 0, y is -1, x is 1, and y is 1, and so on, right? And we know the differences for a linear function, this is a linear function, should be constant, right? And the idea of the differences is the differences is the difference between adjacent y values. Okay, so if I can't see it, I'd go -1, subtract -3. That right there is a little more difficult than it needs to be. Basically, what I think is from -3, how do I get to -1? Well, I go up 2. And I know in this case all of them are the same. So mini conclusion number 1 is the first differences of a linear function, which is degree 1, are constant. Do you remember what happens if it's a quadratic? You have to think all the way back to grade 10. And I mean, you just got to punch in a bunch of values. Look at them all there. Holy moly, what a lot of work. So what I'm going to do is I'm going to help us out a little bit by showing you how to use a graphing calculator to do some of this work too. And then things should speed up quite a bit. There's two ways to help us with, that the graphing calculators can help us with this sort of thing, okay? That's the stuff from last day. I'm going to clear all that crud out. One way is to type in the equation, -3x² -4x plus 1, and then either use the graph, I'm going to zoom standard, say, use the graph, I'm going to hit trace, and then put in -3, and then start using these values, okay, -2, what's that? And so on, fill the values in there. I can also use the table. The second graph gives me the table. And notice that these aren't the values. This is no good. Let's set up the table. Second window will table set, and I want it to start at 0 and go up. This little triangle means the change in the table, how much I'm going up by. I don't want to start at 0. I actually want to start at -3, don't I? And so I'm going to go second function table. And there's the table, and I could fill that in real quick, and there it is. Dandy. Now, I never did it that way. I want to show you an even better way than this. There's a bunch of stuff already in my list. So I pressed Stat and then Edit to get into my lists. And I'm going to put in these values, -3. Say, well, this is already harder than it needs to be. Because I could just use my graphing calculator. Yeah, I know. Just hang on. Watch this. This is going to be awesome. 0, and then what do we go up to? We'll go up to 4. That's fine. Essentially, I can use the stat lists almost as a spreadsheet. If I go up here, what I want the y values to be is this formula where whenever I get an x, I want it to look over into list 1. So this is how it's going to work. -3 times whatever we have in list 1 squared -4 times whatever we have in list 1 plus 1. And then I'm going to press enter. And bam, there's all the values. So I'll hang on, rest all this table business was actually easier, but I want to show you this. This is awesome. And notice we'd have to calculate the differences now, but the graphing calculator will do that for us. So if I want list 3 to be the differences between y values in list 2, so how I do that, I press second function stat, which gives me the list menu, go over to ops, and I'll write these steps down in a second once we get through this. And then I'm going to choose change in list. Change in list. List 3 is going to be the change in list. And I go list 2. And you see the little list 2 character with second function 2. Now when I press enter, bam, they're all there. Whammo. I don't have to do any subtracting. There they are. And notice none of them are constant yet. And if you remember back to grade 10, it's the second differences that are constant. So this row should be constant. And I can just do this again. I can do this as often as I want until they're constant. The change in list 3. And there they are. They're all -6, which isn't that fantastic? Okay, so I'm going to write the steps for what I did there. I went second function stat to get to the list menu. And then I went over to ops for operation, and then I selected option 7, which was delta list. Okay, and the second 2, that gave me the little L2 character. Now that's just to get the differences in lists. I already had to put in this formula up in list 2. I had to put, you know, that in the top of the column, right? List 1 plus, to get that to work. And what do we see? It's all good. Second differences of a quadratic function are constant, just like we knew. But if we extend this now, and that's the lesson today, if we extend that, calculate the finite differences for this. And notice I've done that. I'll go over the steps real quick. They're all there. I'm going to go over the steps real quick here. All those values are, and remember, wherever you are, you go stat 1 to get into the lists, and those aren't the values I want. I want it to be this other function, which is list 1 cubed, so to the exponent 3, minus 4 times list 1 squared, plus 3, press enter, and that's all my y values, all in one shot. I don't have to use my scientific calculator. Of course, you're welcome to if you have lots of time to do these sorts of things. And then I have to do my differences in list 3, which was, I noticed I went up into the column heading, and then I went, not stat, I go, hang on, I'm just going to have a look, make sure everything's good back there. Okay, I'm in the column heading, then I press second stat to get to the list, over to ops, down to change in list, and I want L3 to be the change in list 2. So I put that in there and I press enter. And bam, there's the differences. And then I just keep doing this. I do this a few times. This is the first differences, this is the second differences, and this is the third differences. And lo and behold, the third differences of a cubic function, which is degree 3, are constant. So if you had to guess, if I strapped you to a chair, threatened you with torture to guess about if I had any polynomial function degree n, which differences would be constant, it's the nth. So if it's degree 8, I'd have to do this 8 times, and finally the 8 differences would be constant. Okay? And we'll see this in an example in a second. Now, more stuff about differences. If the first differences are positive, then what's going on? The graph is increasing. And I'll show that in a second. If it's negative, the graph is decreasing. Does that make sense? Notice in this function, go back to my graphing calculator. Do I have that in there? No. I'm going to put that in there real quick. X to the exponent 3 minus 4x squared plus 3. Then I hit graph. Right? And so when the first differences are positive, so for x is negative 3 and negative 2, graph's going up. Then between 0 and 2 and a bit, it's going down. First differences are negative, graph's going down. Then after 4, the graph's going back up. Right? First differences are positive. So that's viable. I think I could get you to believe that. What about the second differences? If the second differences are positive, then the graph is, it's a smile. And that sounds silly, but it's this shape. It's called concave up, is the fancy math term. And then the opposite, if the second difference is negative, the graph is a frown. Going downhill like this. Concave down is what it's called. So back on my example, I'll show you what I mean. Where was it? Second differences. Early on, notice the second differences were negative. Well, there's the frown. Do you see the frown? And then somewhere around x equals 1, x equals 2, it turns into a smile. There's the smile. And then eventually, oh no, it's going to stay a smile. Looks like it's going to stay a smile. Right? So it's got a frown here to about there, I guess. And then it becomes a smile. Next, if the common differences are c, then the leading coefficient is, well, this is a bit of a strange thing. So the common differences is c. Let me just write the ones that we've got. The ones that we saw from the warm-up and the 3-minute review and the lesson so far. If c is 2, that was what the common difference was. It was degree 1, n is the degree, remember, and the leading coefficient was 2. For the second one, the common difference was -6, and the degree was 2. It was quadratic, and the leading coefficient ended up to be -3. So notice we've got, it kind of looks like c might be n times a. Right? You see that? But then the next one, the one from the lesson, kind of spoils it. C was 6. Common differences were 6. But n was 3, and a was, I think it was just 1. So we would have guessed that the common difference is 6. But that's why there's this other little tiny formula. Okay? And it's n factorial times a, where n is the degree, and a is the leading coefficient. Okay, what the heck's that? Well, I called it a factorial. And a factorial is an easy little thing where if we had 3 factorial, that's equal to 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 3 times 4 times, like that. It goes down until it gets to 1. And so we can use this little formula, not often, it's not a big whoop, this little formula, to find the leading coefficient. How am I doing for time? This video is getting long. Okay, I'm going to stop there. Part 1 is going to have 2 parts.